Hi, Syma. How are you doing? I think you've been in London today.
Yeah, hi Tim. Yes, I've just rushed back after a 2 day meeting, so it was a bit of a rush to get back. But coming back to see you is always worth it.
Well, actually, I'm really glad you're here because who we're interviewing today is really quite a remarkable story. It's Omar Yaghi, and he's the James and Nietzsche Tretter Endowed Chair. I think I've said that right. Endowed Chair of Chemistry at the University of California in Berkeley. And he's a chemical magician basically, who from the early 90s has been producing new type of chemicals that some of his colleagues thought couldn't actually be produced in the beginning. And the new materials are made through processes called metal organic framework and covalent organic frameworks. So they're a bit like Lego, aren't they?
Yeah, absolutely. So it's a sort of a combining of metals and organic into into little units, and then they string them together into 2 and 3 dimensions to make very highly sort of defined structures. Yeah, just like Lego, pretty much.
And I think what we'll do is when we talk to him, let's start a little bit about the chemistry. But I think what our listeners are really going to be fascinated by, other than just the chemistry, is the uses of some of these new materials he's making, because they kind of can trap molecules from the air and from water, can't they?
Yeah, absolutely. I mean, it's in a way we might be tempted to think, well, why can't we make anything we want? We know so much about chemistry and about metals and about all sorts of materials, but it turns out that, we can't. And we have things like we know that if you gave me a certain type of metallic rod, I would be able to bend it. And, things have certain properties. And so what they've done with these metal organic frameworks is made things that have never sort of with the kind of properties have never been seen before. So rigid and structurally rigid and strong, but also highly porous, like ultra porous.
But I mean, some of the uses they can suck water out of the air in dry regions to for people to drink and probably even for irrigation. Carbon dioxide out of the atmosphere to
Yeah.
reverse global warming. I mean, they need to scale some of these things. I think we'll talk to him about that. But even storing hydrogen for sort of fuels for cars and things. I mean,
Yeah.
this. I mean, we're really talking about game-changing materials here potentially.
Yeah, absolutely. Sort of our environment changing materials and and in a bizarre way, they work on really simple principles. We all know that, we all sort of it's that sort of old adage, nature abhors a vacuum. If you've got a hole, it's going to be filled, right? There's no, and imagine if you have something that's that highly porous with all those little cavities in it, it actually will not take that much energy to get stuff to go in, right? But they can do that and then control what goes in is remarkable.
But what I think is even more amazing is, he's one of the world's leading chemists. In the 1990s, apparently, he was the second most cited chemist on the planet, or no, in the 2000s, I think it was. Anyway, whenever it was, is, very, very well respected, a highly distinguished scientist, decorated with all sorts of awards. But he actually grew up, his parents were refugees from Mandatory Palestine, which was a British protectorate. And he was born in Amman, Jordan, and he grew up in a tiny house full of siblings and even livestock. So should we start by asking him a little bit about that journey? Because it really
Yeah,
is, it's inspiring. It's incredibly
yeah,
inspiring.
yes, absolutely. I think we should.
Should we get him on?
Yeah, absolutely. Let's do that.
Brilliant. So, welcome, Omar. And first of all, let's dive straight in. So, your background is a really inspiring story. So, if I understand correctly, your parents were refugees in Jordan when you were born, and you grew up in a pretty cramped one-roomed house. So, how did you discover your love of and your affinity for chemistry? It's been quite a journey you've made.
Thank you. It's a pleasure to be here, Tim, and thanks for that interesting question. Yes, indeed, I actually grew up in a one-room house, and in fact, half of the room was filled with cows. These are livestock that we lived off and grew, and in the other half where we lived. I mean, that was really interesting for me as a child. And it sounds extremely stressful at the time when you're going through it. It's just a way of life. I was a quiet child in a very large family, And so I was always sitting there doing my studies and contemplating about the situation that I am in, that I just described. And so, but one day, my break, I think, in life came when one day I went into the library that was supposed to be locked during our lunch hour. And in there, I found a book that had what we call chemists stick and ball diagrams of molecules.
Yeah, yeah.
I didn't know what they were. I just thought, wow, these things look absolutely amazing. I have no idea what they are. They're weird looking. And that got me interested in chemistry. These molecules, it's very likely that they were simple molecules like water or methane molecule. Um, but that experience was very special to me. In fact, I went home thinking I've discovered something that nobody has seen before, or something like that. It's just almost like I went home with a secret.
Sure.
And bit by bit, I became more and more interested in molecules, and it turns out they are the makeup of our body, of nature, of everything around us. And this was a big pull for me. So yeah, that's how my interest in chemistry started. I like telling this story to younger students. They often ask me, "How did you get interested? How do I get plugged into a field? How do I
Mm.
develop a passion for something?" And and the hope, I think, for all of us is that it comes from directions you never expected. And you just have to, I think one of the basic requirements, you have to be observant.
Yeah.
Okay.
And imaginative. I think you have to have that imagination you talk about, right? I think that has
Yeah,
to be key, surely.
sure. I mean, imagination is an extra thing when you start out as a child or as a schoolboy. I think observation is interesting, and then starting to ask questions about what you're observing.
So,
Okay, and
Omar,
that
did you always like that sort of the toys that you played with as a child? Were they sort of building kind of toys, or did this
well,
come from?
ironically, I didn't have toys, and we didn't have Legos, which I later learned that they exist. We used to make our own little toys. But we didn't grow up in a affluent home, so we didn't have the regular supply of games and toys. We kids sort of developed our own toys and our own games. The one thing that I thought helped me quite a bit when I was a child is that very early on, I told my parents that I should be independent of you. Don't tell me what to do. I am happy to do my classes, I'm happy to do my studies, and I will be fine in school. But as long as I'm doing that, I want you to leave me alone. And I think they left me um, to explore on my own. They were very supportive, very loving. And I think that made a big difference in my life.
No, I mean it really is an inspiring story. But despite the lack of having toys, the sort of chemical molecules and new materials you've discovered are a little bit like Lego, aren't they? Really, it's like you're sticking various molecules together to form these much larger molecules that have repeating patterns. I wonder if perhaps you could explain to our listeners in a bit more accurately what the sort of reticular chemistry that you pioneered is really is about and how it really works.
One of the biggest challenges in chemistry when I started out as a student was, how do you build materials in a rational, we used to call it in a rational way, meaning how do I take molecules that chemists are very familiar with working with, and start using them as building units to build larger structures, or what we call extended structures. These are the materials that many technologies rely on. In those days, we used to call it shake and bake chemistry, meaning the way people made materials was they took their starting powders of different compounds and mixed them together and heat them up to 1,000 degrees to make their material. There was absolutely no control. So I was thinking, my proposal for my assistant professor job, my independent research, was to take molecules and use them as Legos. And I wanted to stitch them with strong bonds because I wanted to make robust materials that are not going to break apart when you're using them. And this turned out to be later to be extremely important aspect of these reticular materials, metal organic frameworks and covalent organic frameworks, MOFs and COFs. So that was sort of what was happening as a student was that this intellectually unsatisfactory way of making materials, and I wanted to find a way of making them in a rational or in a design fashion, and building blocks using molecules as Legos was a very sort of natural way for me to think. And so when I started my own lab, we started linking clusters we originally started linking inorganic clusters together, like tetrahedral clusters, and we would link them with these were germanium sulfide tetraadamantane-like clusters that we linked with manganese and showed that you can make extended structures. That paper is a JAX paper that was published in 1994 from my group, my very first JAX paper as an independent researcher. But it was the very first time that someone has used the molecular building block approach to build an extended solid, to build a material. The challenge for doing this kind of chemistry has always been twofold. One is that when you put the building units together, you want to be able, you want to have the chemistry designed in such a way that they can break apart and come back together so that they can orient themselves in the perfect way that you need to make a crystal. And if that process of breaking bonds and forming bonds was not reversible, then the molecules came together, and sometimes they didn't come together at the proper orientation and an ordered fashion. Then you made amorphous stuff.
So yours are quite rigid. So the molecules make it quite rigid, aren't they? They're quite robust once you get those strong bonds correct.
Yes, you want to try to use rigid building units to eliminate as many of those different orientations that are possible for things to come together, but you never can. So you have to rely on the bond breaking, bond forming reactions, and it's almost, I liken it to going into a room full of kids and asking the kids, make a perfect circle. And what happens, if you watch what they do, is that, okay, they hold hands and they're trying to make the circle, but then they break apart. They don't hold hands, and then they hold hands and they try to correct and make that perfect circle. It doesn't happen right away. And that's exactly what happens when you're trying to crystallize a material in general, but also it becomes very, very important when you're trying to build an extended structure when the molecules are linked by strong bonds, as we do in what we call reticular chemistry. So we've overcome that problem by finding the right conditions under which you can have this microscopic reversibility of bond breaking, bond forming, but at the same time, you also have to take into account the kinetics. If this process is too fast, then molecules don't have time to orient themselves perfectly. Okay, you make a disordered amorphous structure. If it's too slow, then you never make large enough molecule to make a crystal. So that's really the nitty-gritty of sort of the big challenge that has prevented chemists from building extended structures using molecules as Legos, and the fact that we wanted them to be stitched together by strong bonds made this challenge even harder. But fortunately, in the mid-1990s, we figured out a way of doing that, and that's when we discovered metal organic frameworks. Okay, so that was the first time where we crystallized a metal ion with an organic linker, and that linker is charged. So now, in addition to the metal ligand bond, you also had charge to charge interaction, and that's strong. So that interaction is as strong as some of the strongest bonds in chemistry, as strong as the carbon-carbon bonds.
So I guess, Omar, just to sort of orient our listeners and viewers, so maybe those who sort of don't have a particular sort of technical chemistry background, I guess the precursor to much of this is what we're familiar with as a polymerization reactions, right? So listeners will be familiar to materials like nylon and such like, so synthetic materials in which linear polymers were first made. And so the great development that you have is these are, of course, extended, they're branched in a very, as you say, rational and defined way, right?
That's right. You've encapsulated that very well. Polymers are 1D, actually polymers are 1D molecules. They're macromolecules, they're very large molecules. We're talking about things that are much, much larger. So large that you can, when they're assembled, you can see them as macroscopic crystals. So a crystal of a MOF, if you're a molecule floating in the crystal, you would be able to move from one side of the crystal to the other side with always walking over strong bonds, covalent bonds, or metal ligand bonds that are extremely strong. So this is a continuous arrangement of stitched molecules, not going just in one direction, but in the second direction and in the third direction.
Yeah.
That's right. And I guess the sort of from a chemical perspective, the other great sort of anomaly or the thing that sort of makes you stand back is this sort of juxtapositioning of metals with organics. So mostly people tend to think of these as two different things, right? You have like a world which is sort of metals, your car is made of metal and all this. We are organic. And so we have this way of using sort of electrostatics and things to bring these two things together in a very powerful way.
That's right. I mean, I think chemists know how to take organic ligands and putting them with metals to make discrete objects like metal complexes or coordination complexes. But beyond that, trying to take these and use them as building blocks, as we have done with MOFs, was just very difficult because it kept producing amorphous or ill-defined material. So what we've done, you can think of it in the following way. We've taken molecular chemistry and extended it to the infinite regime, to the infinite 2D and 3D regime. And it's not just extension of these molecules by repeating them in a solid and linking them through the strong bonds, but also they encompass space. And that space into which basically you can control molecules and transform molecules. So
that's
only not yeah.
I
Not
was
only
that, yeah.
yeah, please.
I was going to say that's one of the reasons these are such an important breakthrough is that these molecules allow you to trap these materials allow you to trap other molecules. So I think these materials you can harvest water from or pretty dry desert air. You can capture methane, hydrogen, carbon dioxide. So there are all sorts of amazing uses for these, and I think our listeners will be interested in some of those. So perhaps we can start with, say, capturing water from dry air. I mean, this is a possible way of irrigating the arid regions, is it?
Yeah. Let me just say before I get to that the power of this chemistry is that because now you can use molecules as Legos, you can assemble them into almost an infinite variety of networks. And these networks are molecularly defined because you can characterize them by single crystal X-ray diffraction. And you know their character on the atomic and molecular level, and they can be designed with precision. And just to give you an idea, we've designed structures that have a surface area as high as 7,000 square meters per gram. Well, that's about a couple of football fields of space entrapped in a gram of material, which is no larger than the US, dollar coin. Okay, so it's in a small amount of material you have encapsulated all this space. Okay, well, this space you can compact gases in this space. Like, for example, early on, we started with hydrogen, compacting hydrogen within that space. Now, how does it work? If you think about um, a bees, okay? Bees, just honey bees and so on. Okay, and I introduce a honeycomb near those bees. What happens? The bees swarm on and concentrate themselves onto that honeycomb. Well, that's exactly how molecules like hydrogen could be compacted inside the pores of MOFs without having to use high pressure or very low temperature, both of which require a lot of energy. So then these materials became extremely exciting for people to try to store gases like hydrogen or methane, natural gas. But also, when you go in and you modify the interior, you could, as we have done recently, you could put in chemical groups that are selective to separating a molecule from many other molecules. For example, taking CO2 out of the air. That's not an easy separation, because for every molecule of CO2, you've got 2,500 other molecules of nitrogen, oxygen that you need to separate CO2 from. So that's a very difficult separation. So we can go into the pores and precisely design them so that we can pluck out CO2 out of the air. And so therefore, we've made some of the probably the best material out there for capturing CO2 from air. It's not a MOF, but it's a COF, a covalent organic framework, which is like a MOF, except it doesn't have metal. The organic molecules are linked together by strong bonds. We have also been able to design structures where their interior looks almost like a grid of hydrophobic centers and hydrophilic centers repeated throughout the crystal. And what happens when you expose this to air, especially arid air, like desert air, Mediterranean air, where the relative humidity in the summer could go as low as 20%, it plucks water out of the air because water goes to the hydrophilic centers, fills them up, and now bridges over through hydrogen bonding over the hydrophobic centers, and it fills the pore. Why am I emphasizing the hydrophobic character of the pores? Because that allows you to control how tightly water is bound to the material.
Okay.
Because after it's bound to the material, you want to release it.
You want to get it out.
So that you can condense it and drink it, right? And so you want to release it at temperatures that are, 40 degrees Celsius, 45 degrees Celsius, what you would have in the desert, or temperatures that you could supply heat from waste heat in industrial installations. You don't have to create or to put in energy to create that heat. And so this is how it works. And the very first water molecule that goes into the pore of the MOF seeds the uptake of other water molecules. It's almost like it is a cooperative phenomena where the very first water molecules opens the way for others to accumulate. And that water molecule, the very first water molecule, we don't even take out when we harvest the water. It stays in the material to attract in the second round and the third round of uptake to attract and behave and create that cooperative uptake of water.
So, Omar, just for our listeners again who are perhaps not so familiar with things, basically what you're talking about is a very, very well-defined, highly controlled, essentially molecular, almost sieve-like material. So it's rigid, but it also has very well-defined cavities in it, so it's porous. And then you can control the porosity, you can control so if it was a sieve, you would be able to control the chemical characteristics of the holes in that sieve. And so you can pluck out selectively, either spontaneously or by providing some kind of tiny energy to pull things out of a material and then also release it. Is that right?
Yes. So in reality, what we have done is we've taken this material to the desert and we configured it into a device, and you have a fan that pushes air into the powder of the material. It's a solid powder. Doesn't look any different than baby powder in this case. This particular case is zinc organic compound. So you push air into the material and only water goes into the pore because water sticks to those hydrophilic sites and builds up inside the pore. And because you also have hydrophobic sites or water, you have water liking regions, that's hydrophilic, and water hating regions, that's the hydrophobic regions. And as long as you can control these two areas and control them on the molecular level, you could also control at what temperature water can come out of the pore so that it can be condensed. And in this case, the water comes out of the pore just by exposing the device to ambient sunlight. So the interior of the device heats up, water comes out of the pores and condenses on the walls of the device, and now you have drinking water, ultra pure drinking water, right? It's the cleanest water you'll ever have. We tested the water for metals, for organics, and it's ultra pure water. We've reported this in our work over the last 10 years.
So I guess
How expensive? Sorry, go ahead, Tim.
So I guess these materials then, not only can you trap, I mean, they have an opportunity to really help humanity here. So not only can you trap water, presumably you could trap hydrogen and then release it for fuel cells for cars. You can help with global climate change by trapping carbon dioxide. Which one? I mean, how far off is it that these things are going to be able to be these materials can be mass produced? Cheaply enough that they really make a difference.
Well, all three applications that you just mentioned, hydrogen, carbon dioxide, and water, are already in startups. And one of the startups has already designed a device, a very energy efficient device that delivers 2,000 liters of water per day.
Wow.
This is now in production stage. They've worked out all the issues with designing the device, the energetics of the device. Everything has been worked out and it's been tested, and it's running beautifully and it's producing at least 2,000 liters a day. This one is electrified, but they also have another device that they are also co-producing at the same time that works entirely on ambient sunlight and on waste heat. And that delivers about 850 liters of water a day. So this is coming very close to the commercialization. The scale up is already in place and the production is already going. So this is something that will be unveiled in the beginning of the next year in January 26. Now, for the same thing is happening with the CO2 capture from air, except here we're in the process of scaling up the material to show that it could be scaled up to multi-ton quantities. So we're working through the chemistry. This is a COF. So we're working through building units, organic building units that are plentiful and cheaper. Right now, the COF that I'm referring to that shows extremely good properties is not as cheap as we would like it to be, but that's the beauty of reticular chemistry, is that once you've discovered one COF, you can discover another one that does exactly the same, but with different and cheaper building units. Now, I should point out that CO2 from power plants or from cement plants is already commercialized. That is already, BASF is producing hundreds of tons for 3 plants in Canada and also in California that is taking CO2 out of cement plants. Cement plants produce about 30 to 35% of their flue is CO2. So they have a lot of CO2 in their flue gas, and they're one of the major industrial polluters or emitters of CO2. So this is an important breakthrough in terms of scaling up the material and in terms of deploying it to capture CO2 before it reaches the air.
So, Omar, could they also, I was just thinking, be used for, sort of cleaning up seawater and such when you have oil spills and this sort of thing? Or would the oil clog up the pores in the MOFs or the GOFs?
Yeah, it's not, they already have good ways of doing that, but potentially you could create We call them oily MOFs. I mean, we have been working on the oily MOFs to allow us to take hydrocarbons into the pores. Potentially, you can design them to do that. Yeah. Once you've figured out a way to making materials and making them in crystalline characterizable form, and you have the flexibility to vary the components, the applications are limitless. Recently, my own group has shown, we haven't published this data yet, but we've shown that you could also take up PFAS from drinking water. Okay. And that's another cough that is able to do that very, very effectively. So yes, you can design the interior for different applications. So this is why recently I've been engaged extensively with developing AI models, high throughput AI-enabled robotics to capitalize on all these applications.
This is amazing. I mean, we're running out of time, unfortunately. So, what I'd just like to kind of ask a slightly different question to finish up with before we thank you. But what advice would you give to a young scientist who's out there in terms of looking back on your career? And I think at times, if I'm correct, early on there was some skepticism that your approach would work, but you clearly persevered. So, what advice might you give to? Do you need to be stubborn, imaginative?
I think we live in the most exciting time to do science. We have some of the best characterization tools. We have tremendous knowledge already on different scientific endeavors. So it's an exciting time to be a scientist. I would say my advice is to do the experiment. Don't theorize about why something is not going to work. Doing the experiment is a lot easier and more fruitful. When you do the experiment, you've opened the possibility for a discovery to happen. And when a discovery happens, depending on what it is, it could change the way we think. It could change society. It could solve societal problems. So doing the experiment, to me, is paramount. So that would be my advice. And don't be afraid to do new things, but do the experiment. Yeah.
Well, I think it's wonderful advice for all of us, I think.
So thank you so much for taking time to talk to us, and congratulations on these breakthroughs. I mean, it really is some of the most exciting science that's being done at the moment, and really has the potential to change the world. And congratulations on the various prizes that you've won recently, which was I was reading about one of the prizes, which is why I reached out to you. It's been an absolute pleasure to have you on, and thank you so much.
Thank you, Tim and Syma. Thanks for all your efforts in this regard.
So I was blown away by that, actually. I mean, really nice descriptions of how the chemistry works, and at one level, it's kind of seems surprisingly simple. You can create this big sponge or this sieve that sucks stuff up, and then you can chemically squeeze the stuff out of it when you want at the end.
Yes. Yeah, but I guess, the vision is to think that could, in hindsight, okay, we can make these things from individual units that we string together, but no one thought that could be possible at the time. It was just not thought of that you could use chemistry in that way. So that initial vision, and I think what struck me was the humility with which he described it, and in a very sort of humble and matter-of-fact way, with a love just for the chemistry.
So why had people thought it was impossible? I mean, it seems the way he describes it. Obviously, I know there's a huge amount of challenges him and his group had to solve to get to this point. But why did people think it was impossible? Because he starts out by telling the story about looking at these kind of these models in a book of molecules. It seems really simple when you say it like that. Well, yeah, why can't I go and grab one of these atoms and join it to another one of these atoms with these bonds? Why is it so hard?
Well, I mean, I guess people could, but they'd make a discrete molecule, right? A single unit.
Like one molecule of water or something, or
yeah, exactly. So we know if we take two hydrogens and an oxygen, you'll get one molecule of water. But then the idea that you could use this as a unit to add another one and another one and another one
Okay,
in
yeah.
a really big and defined way with very, very highly precise spacings between them and the cavities. I think people just thought it would become some kind of amorphous blob.
Yeah, okay. But he found a way of being
Yeah.
able to make really quite large structures.
Yeah, yeah, absolutely. Large and I can't stress enough, very, very porous. They shouldn't be that porous. Something that's got that many holes in it should collapse, right? That's the way we think of
Ah,
it, but they
okay.
don't, right?
That's really interesting. And I mean, we didn't touch upon this, but do you think these have medical, these materials have kind of medical potential, medical uses potentially? Could you make them a little bit sufficiently large that you could suck viruses out of blood or things like that?
I mean, I don't see why not. In terms of, I guess, how if they're metal organic frameworks, then that metal has to be tolerated, I guess, by the body. There'll be toxicity issues, but the other thing is, the scale between chemistry and biology is different. So,
Yeah, okay.
in one of our very first podcast episode, we had Gordon Sangera and Lakmal Jayasinghe on talking about Oxford nanopore, and
Pause.
that's what
Yeah.
it was. But those are tiny, right?
Right.
But if we could get down to that level with these MOFs, actually, you have the advantage over the proteins that are used currently is that these MOFs would be longer lasting.
Right. Okay. Okay. So they're even more robust than the
Yeah, and
protein.
you don't have to put them in a membrane. You could just take them as they are with the holes in, and but can we get them to that level of precision where they're absolutely tiny and all exactly the same? So the signal is coming from when you've caught the DNA in there, nothing else.
Right. Okay. But actually, DNA is quite a big molecule compared to the water molecules that he's talking about when you're sucking water out of. So it
It is, but remember, he's not getting just one water. He's
is
getting
getting lots of it.
loads, and
Okay.
they have to get one. And
Yeah.
so,
Okay. I see. Yeah. Okay. Okay.
mm,
Well, I thought it was fascinating, and I'm really excited to see how this develops over the next few years. I mean, it's really interesting to hear. Kind of it's almost a bit of a scoop that in January they're going to be sort of announcing, or not announcing, but releasing these devices that can remove, pretty staggering amounts of water, in a day from pretty arid regions. And so maybe in a few years' time we'll be hearing about, climate change as a thing of a past because of chemistry. I thought it was trees that were going to solve climate change, but maybe not.
you're such a biologist, Tim. But he made that throwaway comment about the PFAS. So these forever chemicals, what we consider to be forever chemicals in
Mm.
water, and potentially if they can remove those, then you get
And
rid of
clean
this,
up
microplastics and things, right?
and
I
clean
mean,
up the planet. Yeah.
yeah, it could be huge.
What an inspiring man and what an inspiring story. I'm really
Uh,
glad we got him on. So well, I'm looking forward. I'm not sure who we've got on next week, but we'll whoever it is, it will be fantastic. Lovely to see you,
Absolutely.
Simon, and
Okay.
have a good week.
You too, Tim. Take care. Bye.
Okay, bye.